So I wanted to do a little video about rational functions and asymptotes, especially the harder ones. So this is what this is about. So just a bit. So sometimes when we have rational functions like these, um, you'll notice that you have a p and an n, and those p's and the n's will tell us where the vertical asymptote is and the horizontal asymptote is. So Pn, it's always opposite if it's underneath a fraction, kind of like if it's in parentheses, it's opposite. So Pn is where we would write an invisible axis. The P is the vertical asymptote. The N is the horizontal asymptote. If it's in this form, a lot of times it's not. So just FYI. So if we had one like this, the vertical asymptote is right here at x equals 1. And the horizontal asymptote is at 2, and it's right here, y equals 2. And then as long as this is positive and it's in this form, then your graph is going to go through the catty corner point right here and through the catty corner point here, kind of like that. And these get really close to the asymptotes. And we don't even have to graph it with any kind of graphing calculator or anything to know what it looks like. So it's going through 3, 2, or 2, 3, I should say. And it's also going through this point, which is 0, 1. Now, if it happens to be negative, this is our vertical asymptote at x equals 1, because that's opposite. And then minus 2, which is down here, is my horizontal one at y equals negative 2. And then you're going to be talking about, instead of it being in maybe the first and third quadrant, you're going to think of it going through this one, which is the second quadrant, and this one, which is the fourth quadrant. So it's going to look like this. But most of the times they're just asking you what those asymptotes are, and then you can use your calculator to come up with what the graph looks like. Now, sometimes you have 1 over x squared, like 1 over x minus 1 all squared, and nothing changes here. It's going to have a asymptote at 2 and 1. So go over 2 and up 1. So it has a vertical asymptote right here at x equals 2, and a horizontal asymptote right here at y equals 1. And again, these are just the y value and the x value. Huh. And that's how you find those. It seems a lot easier when you see it. And then this is, instead of it being in the first and third quadrant, this is going to be in the first and second quadrant. I call them volcanoes. They kind of look like volcanoes. So you can put a little smoke coming out of the top like that. So that's x squared. Now, whenever you have a polynomial over a polynomial, there's really 3 things that can happen, but I guess possibly 4 things that can happen. Your degree of your numerator might be less than the degree of your denominator. Remember, the degree is this and this. So the leading or the leading term's degree. And if it happens to have a degree that's less than the denominator, then you automatically know that it has a horizontal asymptote at y equals 0. If they happen to be the same, then they're the ratio of the two. And I kind of got into that in that last video. And then if it's 1 bigger, you're going to have an oblique. So they're really these three, and then the fourth one is kind of a, so we'll refer back to this. It's what a reading to, and it just doesn't make a whole lot of sense until you see it. It's always going to be the degree. So this one, you notice the degree is 2. The degree of this one is 3, just like that. So the degree of the numerator is less than the degree of the denominator. And if that's the case, we know that it has a horizontal asymptote. Horizontal is like the horizon at y equals 0. We also know from the denominator that it has, if we factor this denominator, because that's how you find out when it doesn't equal, or when it can't equal 0 is where the asymptotes might be. So if I factored out x squared, I'd have x minus 2. So x cannot be 0 and x cannot be 2. These are where it cannot be. So these happen to be our asymptotes. So at 2, you have a vertical asymptote, and you have a vertical asymptote here at x equals 0. And then what else happens is you have a bunch of other graphs, and you'd have to plug in a lot of terms to get those graphs. So what I'm going to do is I'm going to escape out of this, and I'm going to go right to Desmos. And I've already printed these in. And I want you to kind of look at this. Now I'm going to take this off the screen because this is what the graph looks like. And we said that it had a horizontal asymptote at x equals 0, or y equals 0, I'm sorry, and then it had a vertical asymptote at y equals 0. So that's just right here. Now the asymptotes are not part of the graph. They're just boundaries that they can't cross. So 2, it never gets to 2. It never gets to 0 here. So there's just these boundaries that kind of work. So that was the first one. And so that's what the graph would look like. And if I go back to this, we know that it had an asymptote right here, and an asymptote at 2, and a horizontal one here. And I believe it did something like this, oops, and like this. Then it had something that did this. So anyway, that kind of gives you what the graph looks like. So what happens if the degree of the numerator is the same? This is what we're talking about. This 2 and this 2 are the same. Then you're going to have a horizontal asymptote right here at the ratio of the leading coefficients. So 5/2, which is 2.5. So over here at 2.5, I want to make it dotted, we'd have a boundary that it can't cross. We also, down in the denominator, we would have 2x squared minus 2. We set that equal to 0. And we can use the square root theorem on this one. Take the 2 to the other side, divide by 2, x squared. You could have factored it also. And then take a square root. So you'd have x is equal to plus or minus 1. And so, it has vertical asymptotes. I'm sorry, we did this incorrectly. I did this incorrectly, which is good for you to see. I always say that. No, it's not good. But so this one is y equals 5/2 is the horizontal asymptote. And then it has vertical asymptotes. Come back. That x equals -1 and -1. And then what is going to happen is These are just the boundaries that they're asking you where those asymptotes are. So again, if we go and escape out of this and go to Desmos, I have it written in here. So this was number 1. This is number 2. Let me take one off. And you see that the line can't get any bigger than 2 and I'm looking at 2.5 is right here. So 5 halves is 2.5. So it has a vertical asymptote at 2.5. What did I might have typed it in wrong. That's always an issue. Is this one? Doesn't seem to be. Well, it's supposed to have a one at 5 halves, a vertical horizontal asymptote at 5 halves, but this one doesn't seem to look like it does. Because 2.5 would be right here, and that would be straight across, and that's not right. But it does have a vertical asymptote at 1 and -1. But oh yeah, it is at 2.5. This is 2.5. I'm sorry. If we look at this, these are it. I just need to make this a little bit bigger. There you can see it. Between 2 and 3 is 2.5, so it doesn't get any wider than, or it gets really close to that horizontal line. So we're good there. I just wish I could write on. Oh, I can write on it. So see how I am. So it can't get any bigger than this. This is the horizontal y equals 2.5 or 5 halves. You would want to put it as 5 halves, and then it has vertical asymptote right here at x equals -1, and then another one at 1. But a lot of the questions are asking where these vertical and horizontal asymptotes are. You should find them first before you start to plug in numbers or even look at the graph sometimes. So just kind of putting that out there. But let me clear this. Okay, so the next question is this one. And notice that the degree is 1 up here and degree is 1 up here. So it's just going to be 10 over 4, which is 5 over 2 again. So it has a horizontal asymptote at 2.5. So it's going to be going like this. And then if we take our denominator, this is kind of confusing because when we solve this, we're going to get 2x is equal to -10, divide by 2, divide by 2. Oh, it's 4. Yeah, that's what I meant. 4, divide by 4, divide by 4. X is equal to -5 halves. So it has a horizontal asymptote at y equals 5 halves, and it has a negative, a vertical asymptote at -5 halves, which would be right here. So x equals -5 halves. And I went ahead and graphed that one too. So we'll go look at it really quick. Put that there. And I know the thing's on the screen, so I'll go ahead and clear that off. And so we have at 2.5, which would be right here. You can't really see unless you stretch it out. And then at -2.5, you have a vertical asymptote going like this. So hopefully that helps with those. So the next one, you'll notice if I have it right here, is that the numerator is, the degree of the numerator is bigger than the degree of the denominator. So the third case, this is when it's going to have an oblique asymptote. And to figure out what that oblique asymptote is, which when I was sitting in your seats, I I just totally missed these. Just being honest with you. I just I struggled with it. So here's the problem. And what you have to do with these is you have to long divide them. You can't use synthetic because it's 2x plus 3, which is unfortunate for us. So we have to go long division. So we put in negative 2x, get negative 4x squared minus 6x. Change your signs, and you're going to get 0, and then you're going to bring down the 3. So let me erase this. Let's erase that and just put a 3 down here. So the remainder is 3. That doesn't matter, but what this exponent, or what the divisor is, what we get as an answer, I should say the quotient, is y equals negative 2x. And that is a graph that would go on our page. So I'm going to remember that because I can, and I'll go back to our Desmos. And I'm going to take this off, and I'll make a new graph, y equals negative 2x. So that is the asymptote, y equals negative 2x. And if I was to graph this one, and it's this fourth one down, and I click on this, you'll see that it doesn't cross that. So it has what we call oblique asymptote going through there, that blue line that you see. The other one is kind of curving off towards it on the left, and then on the right, it's curving towards it. So as this gets closer, and on this one, it's getting closer on that side. So whenever it's just one difference between these two powers, so the degrees, the powers, there's only one difference between them, then you're going to have an oblique asymptote, and you need to divide them. Now, as soon as you go, let me take these off. This one and this one. Now, if you notice this one has two differences between it. And in that case, according to these rules up here, if they're two different, then it's going to have a power function, and it goes off of the leading coefficients and then subtracting the powers. Confusing, I know. So in this problem, you would have the leading coefficients 2 over 1. And then if you subtract it, you're going to see in this equation y equals 2x squared. So when I graph this, you're going to see that. And you see it kind of here. You're also having this graph coming down here. But it does have a vertical asymptote. It doesn't have a horizontal, no horizontals. And that's the one thing I should have said, is no horizontal asymptote. But the denominator has one, and it's, what is that? X cubed is equal to 1 when you solve it for 0, or let me just write it out. So I have x cubed is equal to 0, then take the equal to 1 when you take the 1 to the other side, and then take the cube root of both sides, and you'll have x is equal to 1. So you'll notice that it has, this is 1 right here, because 0, 2. So it has this vertical asymptote right here at x equals 1. So always look at your denominator for that vertical asymptote. It's always the denominator. But then when you're trying to find the horizontal ones, whether they have them, or if there's not multiple ones, but if there's one, or if they're oblique, you have to know when, your numerator is bigger than your denominator. If your numerator is the same as your denominator, degrees. So clear out that. Now this last one is this one. And thanks for sticking around with this. We know that it cannot be 4, because if we put a 4 in here, we're going to get a 0. But if we factor this, the numerator, we're going to get x minus 4, x plus 1 when you factor it, because you try to factor that numerator out. And the numerator is bigger than the denominator. So you think, oh, yeah. So it's going to have whenever your numerator is bigger than your denominator, it's going to have a horizontal asymptote at 0. This one doesn't. So this is an anomaly, because when I factor the numerator, these two things are going to cancel out. And really all this function is x plus 1. So it's crossing here at 1 and going up 1 over 1, up 1 over 1, up 1 over 1. And so we have a graph that goes like this. But we also know that it doesn't have a whole, or it's not defined at 4. So over here at 1, 2, 3, 4, there's a hole. That's an open. So the graph goes along and it's just not defined at that hole. So there's like a hole right there. And if I go to Desmos, this is the cool thing. I enjoy this. This is the one thing I like about it. If I go to Desmos or your graphing calculator and you cursor up to it, so let me get this off and I'll put this one on and I'll kind of move this around a little bit. I'll get all those things off there in a second. Okay. Move that over. And let me clear off all this stuff. Okay, so that's the graph. And you're like, oh, that's just a straight line. Well, if we go over to 4, whoa. So let's go over to 4 and go up to the line and kind of click on this. Notice that as I bounce across, but when I get exactly at 4, it says it's undefined. And that's the reason it's not defined at there. So a lot of times they're going to ask you what the domain of these are. So there's a hole right here. And so the domain is a parenthesis, I should say, 4 going to negative infinity as you go this way, and unioned with the 4 to positive infinity going that way. So this is the domain. Now, I guess if they asked you the range, same things would happen, but it's going to be 5. So it would be, you always go with a small number first, negative infinity to negative, or to 5, I should say. And that's going this way to 5, and then unioned with 5 to infinity. And because we use parentheses here instead of brackets, it doesn't include those points. So hopefully this helps a little bit. Thank you for sticking around to watch it because it's kind of long, but knowing those different types, where when the numerator is bigger than the denominator, it's usually going to be looking, clear out this. It's usually going to happen. It's going to look like this or something like it. It's going to have vertical asymptotes, but its biggest thing is the horizontal asymptote is at 0. As soon as we take that one off and go in them equal, when the powers are the same, then you have the ratio of 5 to 2. And the same with this one. This is 5 to 2. So it's going to have one at 5 halves. And then if the numerator is bigger than the denominator, the degrees are, then you're going to have a oblique asymptote. And if it's too bigger or even more, then it's going to do other things. It's going to have different characteristics happen to it, like this. And has no horizontal asymptote because the biggest thing is we're trying to find the horizontal asymptotes. There's none of them. And then the final one is if it can factor down, it might be a straight line and it's not defined. And I would make sure I know that's for the test because I believe there's something like that on there where you have to factor the numerator and cancel it out, and then it's going to be wherever it's not there. So hopefully this helped, and thank you for listening.